This is a special request to look at question 6, which was one of the harder ones on that rates of change work. Again, they are tricky questions, they're quite big questions, and this one had an extra little trick that's a bit nasty in there. So they give you the formula in this one. It's the value of a car. Again, it's question 6. The value of a car is 10,000. It's all in pounds, times 1.5 to the power of minus t. So this is, although we are used to seeing exponentials in here, this is just a kind of rates of interest depreciation kind of formula. If we were to sketch it, and we don't have to sketch it, I would say it's probably depreciating down to a value. And the value it's depreciating down to is 0. So it's got an asymptote at 0. So it's got this basic depreciation curve. The minus next to the t is what has swapped it round from being an exponential equation. So we're used to seeing that exponential shape. The minus sign up here transforms it, flips it around the y-axis. Or the v-axis in this case. Okay, so don't worry too much about that if it doesn't make sense. Some people it adds some interest. So we're finding out the value of the car on the 1st of January 2005. I'll let you do that bit, part A, because that's just working out what t is. T is in years. So 1st of January 2001, 2, 3, 4, 5. We're 4 years on, so we've got t equals 4, so you can just work that out on your calculator. Part B is differentiating this thing. So part B is inviting us to find dv dt. Yeah. So we're not changing variable in this one, it's just rates of change, just a difficult differentiation. I will try not to put anything like this in the assessment. But there is a method. So dv dt, if this was an e to the power of t, it would be really easy, but it's not because of this. But there is a way we can convert that, and there is something on your formula sheet that will help if you find that one. So let's look at this, this kind of equation, and if we want to differentiate it, it would be great if we had it in terms of e to the power of something. So we can introduce the exponential, we can introduce natural logarithms. If we take the logarithm of both sides, (10,000) 1.5 to the minus t. This is a trick to take this apart and make it into something more friendly. So if we completely take this apart, we need a couple of log rules here. We can separate the 1,000 and this bit. So that's 10,000 add the log, the natural log of 1.5 to the power of minus t. And then this thing, when it's raised to the power, we can bring down the power. So second log rule, hopefully you'll remember, we can do minus t ln 1.5. And this is when we do have this exponential growth or decay kind of curve. This is an amazing trick to turn it into a linear equation where you can just plot ln v against t and you'll get a linear relationship. But back to this problem, we aren't much closer to finding dv dt, but what we can do is now undo what we did before, and we'll get, so the opposite of lunning is just putting everything to the power of e. So I can do e to the power of ln 10,000, which is just a number, minus t ln 1.5. Looks horrible at this stage, yes, but this is just v, so I've done the inverse function. And on this side I can split these. When I've got two subtracted powers, again I can do the opposite. So this is e to the ln of 10,000 times e to the minus. Okay, so give me a moment just to absorb that. I've just treated this like an addition rather than a division by leaving the minus t up there. Okay, so this is the trick, is we ln it, we split the complicated side apart, and then we raise it back to the power of e. And what you get then, well, e to the power of ln 10,000 just goes back to being 10,000. So it hasn't made any change to this first bit. But this second bit, it has. We've now got e, and we're going to leave it like that, e to the minus t ln 1.5. Now 1.5 and the ln of 1.5 is just a constant. So we've got e to the something times t. Remember, sometimes we have a function e to the minus kt, something like that. So this we can differentiate. So it is a bit of a trick, but we can now differentiate with respect to t. The 10,000 stays the same as the constant at the front. This doesn't change because it's now an e to the power of something, but what we do have to do is, if we differentiated this, we would get a minus k right at the start, and exactly the same here. This ln, in fact minus ln 1.5, is going to have to come down to the front. So we've got minus ln 1.5 times the whole thing. Okay, so this enables us to work out what we've got. We could substitute this back in, this e to the minus t. We could take this bit out and move it back to the original, but it's quite useful in that form. Okay, so there's dv dt, and the question actually gets us to find an exact value when t is 4. What is this? t equals 4. So we don't have to manipulate this anymore, we can just put it in our calculators. T equals 4, and off we go. So we get dv dt equals minus ln 1.5, that's just a number that your calculator will give you, times 10,000, and times e to the minus 4 times ln 1.5. So complicated to put into your calculator, but these are all numbers and we'll get a value out at the end. I think that's on the mark scheme, what you get at the end there. What does it represent is part of C. So what we've actually found there is the gradient of this brown line here. So that's our dv dt here, not that one. So what we found is the rate of change, isn't it? It's the rate of change of the value of the car, or its depreciation, if you like, is given by that. And certainly this is, after 4 years, we've worked out the value in part A, and this is how fast it's decreasing, how quickly that value is dropping per year at that point. So yes, so just needing the phrase rate of change somewhere in there to nail that. Anyway, I hope this trick does come up sometimes, that we need to learn in order to get things in terms of e to the t or e to the x. It's really useful when we're going to differentiate or integrate, because e to the power of something we can do, 1.5 to the power of something is trickier. have a little look on your formula sheet, and there is a little formula. So last thing to look at, see if you can find this formula that a to the x, this thing, can be rewritten, where is it, as e to the minus, e to the x times ln a. So that's a little formula I think that they give you. So you can just quote that if you like, if you write that on your page, and if you can see what your a and your x are, you can just pop them into your formula. So you don't have to, this enables you to skip down to this point here really quickly. So you might want to label what your A is. Don't forget your constant stays on the front. If you can label up your A, you can use this formula to cheat and get down to there really quickly and get all the points. Okay, hope that helped anyway. Hope you're enjoying your day, and we'll put up some integration questions tomorrow and see how you get on. Let me know if you need any help. Bye.